Hello and welcome. Recently, I have dived into the MAME source, I have recently divin into the MAME. Hello and welcome. Recently, I have been reading through the MAME source code in an attempt to fix a bug that has been plaguing me. I've never looked at the MAME source code before, and in fact, I've never looked at any emulator source code before. I've always wondered how they work and what they look like. So what I'd like to do in this video is to show you what I've learned and show you how the code is structured and what it looks like. But please keep in mind, I am a complete beginner to the MAME source code base, so please don't look at this as some kind of expert explaining how everything works. It's really just a beginner giving a glimpse of the code to anyone who's curious what it looks like. Before you continue, you might want to take a look at this video where I talk about interrupts on the 6809, because we will be using interrupts as a way to kind of walk through the workflow of a particular scenario in the MAME code base. But you don't have to watch that video if you don't want to, because you are free to do whatever you like. Let's go. The general rule of thumb is that for any machine that MAME is emulating, each chip is going to be represented by its own C++ class that emulates its behavior. So if we go into this devices folder, we'll see there are a few different kinds of devices that it can emulate. If we go into video, we'll see a long list of all of these different kinds of video chips that it's able to emulate. And of course, if we look closely enough, we'll find our good old friend, the 6847 VDG on the CoCo. And if instead of video, we go into the machine folder, we'll find all sorts of chips that are available on machines, including our good old friend, the PIA, the 6821. And of course, as you would expect, there's a whole bunch of CPUs in here. So if we go looking for our 6809, from Motorola, we have its folder here. And then there are a bunch of files related to that. And you'll see there's the 6309, it has its own class. And for the CoCo 1 and 2, the 6809 over here. Bringing everything together, there's another MAME subfolder. All these different overall machines, an unbelievable list. And if we go down to TRS, here's where we find the different versions of the CoCo and the Dragon. And you can think of these like wiring diagrams. So for example, here is the CoCo class, which represents the CoCos 1 and 2. And the constructor gives us an idea of all of the fields that need to get initialized, including an emulation of the cassette, or of the cartridge port, the screen, the two PIAs, the Becker ports, IRQ and FIRQ pins. And here you'll find functions like this. So what happens when the programmer writes to location FF20? Well, the CoCo, which is coordinating all of its chips, is saying, well, I know that that's wired up to my PIA1, and so I'm going to propagate that right into the PIA1. A subclass of the CoCo state is the CoCo 1-2 state, which is used for even more of the details for the CoCos 1 and 2. For example, you can see the crystal that drives the whole computer initialized here. And down here you can see the two PIAs getting wired into all the different hardware that controls them. For example, the first PIA you can see gets wired into the IRC, and the second PIA gets wired into the FERC. And there's of course a class that represents the SAM. And we wire up the cassette and the serial port, and it gets wired up to both a screen device and the 6847 VDG. And as we'll see later, the VDG, which is capable of notifying its clients of an H-sync or an F-sync, gets wired into these functions that sit on the CoCo 1.2 state. To see how different components fit together, we're going to take a look at what happens for an interrupt, in particular the field sync interrupt. We start in the VDG in the 6847, and there is a timer that goes off when we hit the end of each horizontal line. At that point, we ensure that we've finished having the screen render the rest of that line, and then we go here to the next scan line. This function keeps track of where we are inside of the frame, and it keeps track of the zones. So we've got the blanking zone, the retracing zone, the top border, the bottom border, and of course the body. After we've advanced to the next scan line, then we decide if we're near a field sync, if we're entering the falling edge or entering the rising edge of the field sync. And if so, we initiate another timer that will go off on the very next line when that field sync interrupt is supposed to go off. Now I actually have the debugger broken at the point where that goes off. So let's see what that looks like. At the very bottom of the stack, you can see that all the components are given their own time slice to do a little chunk of work. And this is how crystals and clocks are emulated in MAME. I don't know exactly how this all works, but somehow each piece of hardware, the CPU, they can do a tiny chunk of work based on how thick that slice of time is. And that brings us up to the VDG. So at this point in time, the VDG's change field sync timer has gone off. And that means we're either transitioning from rising to falling or falling to rising edge. And then there is a callback that the VDG has to notify any pieces of hardware that have subscribed to that callback. And going up the stack, we can see that the component that subscribed to that callback is none other than the CoCo itself. So when the field sync goes off, the CoCo wiring, in a sense, is notified, and it tells PIA0 that the CB1 signal has changed. And this tells it what that state is. Has it gone up or gone down? That brings us into the PIA so that it knows that it can update its state to account for that interrupt that just occurred. And in particular, this is going to be interesting. So let's advance to this breakpoint here. I believe what this does is it changes the state so that the next time the CPU gets a time slice, it will know that a signal has come in to tell it about an interrupt. So let's go ahead and take a look at what the CPU does when it recognizes that signal is active. This is the code that emulates the 6809 itself, and you can see the code is divided up into various states that tell it what it needs to be doing next. Right now we're in a state that's numbered 50, and take a look at what we're doing. We're going to the condition code register, and we're masking the IRQ. We're masking the IRQ. That is the first step that the CPU does when it receives an interrupt. Let's keep going. We enter the standard IRQ callback function, which is actually defined on a base class. It's got a few steps. The step that I was most concerned with was over here. This is where it goes to the MAME debugger, the 6809 debugger, to alert it that an interrupt has happened. Before we get there, though, we need to know the vector. Where are we supposed to jump in response to that IRQ? Once we get that vector, we're going to return it. And then we're going to advance to the next state where we can populate the program counter with that new vector. So if we keep stepping, we can actually take a look at the values of the registers in the 6809. And you'll see we've got all the registers right here. So let's take a look at the program counter. L and H surely must mean low and high. And sure enough, O1, OC is what we're populated with, and that is the known vector for the IRQ. And so that covers the short walkthrough of the flow of an interrupt that eventually causes the CPU to jump to its vector. And I hope this gives you an idea of the scope of this project and how thoroughly each piece of hardware is emulated in software. And what's nice is that the architecture allows each component to be reused in other machines that happen to reuse those same chips. So for example, the various Dragon machines get to reuse many of these same components, like the 6809 and the PIA and the SAM. And they might be using different clocks, and they might be wired up in slightly different ways, but they get to make use of all the work that went into that other hardware to emulate them. And we haven't even really scratched the surface. We haven't talked about sound, how the SAM controls everything, the cassette tape, virtual hard drives, joysticks, the floppy drive controller, even third-party devices like the Glenside IDE adapter, the Orchestra 90, the WordPack word processing cartridge, which comes with its own video device and screen device connection, and many, many more. The scope is truly staggering. So I hope this gives you just a bit of a taste of what goes into emulating the CoCo and all of its hardware and all of its products that folks have bought throughout the years. Still to come on this channel, I plan to talk more about the bug that I have been attempting to fix and what went into that.